I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the welding of metals. This is the second presentation on the solid state joining process, and in this particular presentation I will be talking about the mechanisms associated with the solid state joining processes and the few solid state joining processes with regard to the principal and the process parameters. Okay. So, this presentation includes like the mechanisms, diffusion, recrystallization, mechanical interlocking, localized melting and the melting which is realized in some of the cases like in diffusion brazing. Okay. In localized melting sometimes it happens in under unfavorable conditions during the ultrasonic welding. Okay. While in other cases there is no melting in the solid state joining processes. Then the common solid state joining process about which we will be talking in this presentation with regard to their principal approach and process parameters is friction welding, friction stir welding, ultrasonic welding, diffusion bonding and the roll bonding. So, these are the two, actually you can say that these are the two variants of the diffusion bonding. So, the one thing is this like the metallic bond generation. So, when the two components being to be joined by solid state joining process, they need to be finished to such an extent and they are cleaned to such an extent that when they are put together under pressure, the at the interface the two surfaces come close to each other at atomic level. Okay. So, once they come close to each other at atomic level, the atomic attraction of force helps to bond them. So, electrostatic force between the anions and cations that mainly contributes for the metallic bonding. The diffusion bonding, so in case of the diffusion what happens, like when the surfaces are in perfect metal to metal contact. So, because of the compositional difference, because of the difference in the concentration of the allying elements, atoms diffuse from one side to another and that in turn helps in development of the metallurgical bond across the interface. Okay. And since the surfaces are also will also be experiencing the micro scale plastic deformation. So, when things deform plastically even at micro scale at a high temperature, new grains are formed through the recrystallization. So, the diffusion across the interface will facilitate the recrystallization and formation of the new phases, okay, depending upon the constituents which are there. But it is very important that the finish of the surfaces is extremely good and the surfaces are cleaned. Okay. Now, the localized and discrete melting at the interface for metallic intimacy. Say in diffusion bonding sometimes what happens, like the surfaces are usually rough, okay, both the sides. So, it will take very high pressure to ensure the perfect metallic intimacy and that may not be very viable option. So, what we can do, we can at the interface we can put the interlayer. Interlayer can be a soft layer, the low melting point material. Okay. So, when the things are heated, this melts and fills the gap, okay, and that ensures the metallic continuity. So, this approach is particularly used in case of the diffusion brazing. Okay. In diffusion bonding what happens, interlayer remains in the solid state, but under pressure it fills the ups and downs which are present at the surface. Okay. Recrystallization is about the formation of the new grains and which is usually in solid state joining is coupled with the deformation. And why does it happen? Because when there is a plastic deformation, whether it is a micro or macro level, this and some heat is generated under in situ conditions. So, heat generated coupled with the plastic deformation facilitates the formation of the new grains through the recrystallization. Okay. And the mechanical interlocking in the processes like the forge welding and ultrasonic welding, where the interfacial deformation, explosive welding, magnetic pulse welding, where interfacial deformation is such that the surfaces from the two sides they deform like this. Okay. And that is how they develop the metal to metal interlock, okay, mechanical interlock. So, under these conditions when we apply stresses, this the wavy structure acts as a mechanical interlock and that in turn helps in increasing the joint strength as compared to the case if we have the flat interface, then it will be offering little lesser strength as compared to the case when we have the wavy interface, and this is particularly true for ultrasonic welding, explosive welding and magnetic pulse welding, okay, for these three processes. In mechanical interlocking, in forge welding is altogether different, where macro scale plastic deformation is involved and that contributes in development of the good joint. We will try to see these mechanisms little in more detail, like say the two different metals, okay, having their own atoms both the sides as per the composition, and there is a aerial gap. So, of course, it cannot diffuse, they cannot come very close together when the two are separate, and but when the surfaces have been finished, smoothened and cleaned and under pressure, when the two components are brought close to each other, they come close to each other at atomic level, and when this happens through the atomic attraction, the bond is developed for the metallic bonding. In solid state joining, say the diffusion bonding, where like the components in the beginning when they kept separately, this is the micro aspect atomic level schematic representation, when they are put together in close contact. So, there is metallic intimacy at atomic level, and once this is developed under the favorable conditions of a high temperature coupled with the good metallic intimacy, the diffusion of atoms from one side to another takes place, and that in turn helps in development of the metallurgical bond through the recrystallization, forming new phases and then the grains at the interface. Localized melting, or you can say the melting in a controlled way, that is particularly used in case of the transient liquid phase bonding. So, in that case what we do, we use intentionally the low melting point filler, okay. This is one, or we choose the filler such that it interacts with the parent metal to cause the eutectic reaction, so that the molten metal is produced. When the molten metal is produced, it will be filling the gaps, followed by the diffusion of the elements from this layer, and eventually this layer will get diffused out completely from the interface to develop a sound metallurgical bond. But in case of if the welding or the joining parameters are inappropriate, like in ultrasonic welding, then it can cause the localized melting here and there. And but whenever there is unintentional localized melting here and there, so this melting degrades the joint performance, especially in case of the ultrasonic welding or the explosive welding or magnetic pulse welding conditions, okay. So, this can happen due to the overheating, or this can happen due to the abnormal set of the process parameters which are being used. So by optimizing the process parameters of ultrasonic welding, magnetic pulse welding or explosive welding, we can avoid the localized melting, which is undesirable. But in transient liquid phase bonding, where the interlayer is selected in such a way that it forms the it leads to the either peritectic reaction or eutectic reaction through the interaction either between the with the one of the parent metals to produce the molten metal and fill the gap, which will subsequently diffuse out completely. So, initially let us say this is the interface. So, we will be putting the interlayer like this, okay. This interlayer coming in the molten state, then the diffusion of the elements from this will be happening, and gradually this interlayer will be completely diffusing out from the interface. So, whatever the interlayer has been used to facilitate the diffusion brazing, that will be diffusing out completely if we give sufficient time, otherwise concentration gradient will be left like this. So, if we keep on increasing the time for diffusion brazing, then this will be reducing the concentration gradient across the interface, okay. This is about the recrystallization. Initially the components are different, when these two come very close to each other coupled with the plastic deformation at a high temperature, new grains at the interface are formed, and that in turn results in the metallic continuity without any distinct layer or zone where of the interface, okay. This is about the schematic of the mechanical interlocking. As I have said, like say in case of the ultrasonic bonding, initially the surfaces are like this, and when the ultrasonic welding is carried out or the magnetic pulse welding is carried out, it can lead to the development of the flat interface, or it can also lead to the development of the interface which is wavy, or it can lead to the development of interface which is jetted like this, or it can lead to the interface jetting coupled with the localized melting at the root. So, depending upon the severity of the conditions which are being used, we can have these 4 variants of the interface morphologies during the ultrasonic welding, magnetic pulse welding, and explosive welding. Okay. So, it can be flat, it can be wavy, it can be jetted coupled with the localized melting, and either side further, if the parameters are not appropriate, then there may not be any bonding, no bonding either side. Okay. So, it is important that the process parameters are optimized properly. Okay. So, as far as the solid state joining processes are concerned, there are 4 or 5 processes about which we will be talking. Let us say the friction welding, friction stir welding, ultrasonic welding, okay, roll bonding and diffusion bonding. Okay. So, starting with the friction stir welding. So, here what we do, like say the friction weld joints can be developed in the 2 configurations. One is the butt joint and another is the lap joint. Okay. The approaches are different in these 2 cases. In the butt joint, like say we use a non-consumable tool with shoulder and the pin at the interface. So, what we do, the tool is tool, say this is tool with the shoulder and this is the pin. The tool with the pin is and shoulder is rotated. So, initially what we start with, tool is rotated and then gradually it is plunged at the weld line. Okay. Once this is plunged gradually, a rotating tool is plunged gradually up to the near the bottom zone. This will be causing the 2 things. One is the frictional heating and the second is the heat generated due to the plastic deformation. So, heat generation due to the friction and coupled with the plastic deformation will be causing the softening of this metal. Okay. Softening of the metal near the tool pin wherever it is. So, the heat will be generated at the top by the shoulder due to the rubbing of the shoulder with the top surface of the base metal and the vertical surfaces and the bottom surface of the pin. So, basically the frictional and deformation heat contributes to the thermal softening of the material. Once the material has been softened, then it will start flowing from one side to another, from the leading edge to the back side and trailing edge or trailing edge to the front edge, and this in turn leads to the movement of the material from one side to another to develop the metallurgical joint. So, in this process, this severe movement of the material will be causing the plastic deformation, okay, coupled with the heat generation, so causing the high temperature. So, since the temperature is high and the deformation is happening due to the rotation of tool, what it causes? Dynamic recrystallization. Okay. There is dynamic recrystallization in the weld zone produces very fine and equaxed grain structure. This is very common thing which is observed in all kind of the metals, followed by the solid state transformations that may occur as per the kind of thermal cycle which is being imposed. Okay. So, this is about the butt joining. So, as far as the steps are concerned, the first is the rotation of tool, then plunging of tool, okay, gradually lowered along the weld line, and then dwelling. The tool is continued to rotate at a particular location so that enough heat is generated for thermal softening, and then tool is moved along the weld line, that is called traversing, so that the joint is developed along the weld line, and once the joint is completed, then tool is retracted. So, retraction of the tool. So, these are the like say 5 important steps. Okay. But in case of our the lap joining, the steps are little different. Okay. and say this is the, so there in lap joining, so there is a lap configuration, this is the plate A and this is plate B. So, our rotating tool, like say this is the tool pin and this is the shoulder. So, the tool is rotated, gradually it is lowered. So, it will be penetrating first the top surface reaching up to the bottom, partially penetrating the partially to the bottom sheet also. Okay. So, once this is done, penetration is done partially, maybe up to the half of the lower sheet thickness. So, this is done, then thereafter traversing is done for developing the lap joint. Okay. For the lap joint, lap seam joint, you can say lap seam joint. So, in this case what the kind of thing that we will be getting is like this. So, our joint in the top will be developed, the joint at the top will be developed all along this the length. Okay. So, and at the end the tool will be retracted. So, it will be using the steps like the tool rotation, okay, then plunging and then dwelling, then traversing, okay, and then retraction. This is true for the lap seam joints, okay, where the continuous joint between the two sheets is developed along the weld line. But if the joint is made little differently in lap configuration, like say this is the top sheet and the joint is made just here, this one in the top view if you see. So, it may look like this, okay. So, here it may look like this. So, here we may have one spot here, another spot here. So, in that case our tool will be penetrating partially at one location, then at another location. So, in this case it involves just the rotation, plunging, dwelling and retraction. There is no traversing because we need to just create the spot at a particular location. So, this is about the butt joining, lap joining, whether it is a spot or it is seam. So, these are the two variants related with the lap joining using the friction stir welding. Okay. So, the how the heat is generated, say the tool is rotated, as I have said, this is the tool. If it is rotated at a very high speed like say 500 rpm or 1000 rpm. So, the rate of heat generation due to the deformation and friction, that will depend upon the rotational speed of the tool. So, rotational speed of the tool basically decides the rate of heat generation. Okay. Then the second is traverse speed, how fast the tool is moving along the weld line, like say this is the weld line. So, the tool is moving at the speed of say 20, 30 per minute or 100 mm per minute. Okay. So, since if the for a given rpm our rate of heat generation is fixed. So, if you are moving slow, then lot of heat will be delivered to the base metal for development of the joint, but if you are moving fast, then heat being delivered to the base metal, that will be reduced. So, means increasing the welding speed, traverse speed will be reducing the net heat input, and reducing the traverse speed will be increasing the net heat input, that is all. Okay. And now, as far as the tool geometry is concerned, there are two important aspects related to the tool geometry. One is the tool shoulder diameter, okay, and then tool pin diameter. So, these are the two important aspects. Apart from that, there can be many other variants, like the tool can be cylindrical, tool can be square shaped, tool can be threaded, tool pin can be conical. So, there can be or conical coupled with the threaded. So, there can be many variants as far as the tool pin geometry is concerned. So, the tool shoulder and the tool pin diameter, these are the two very important aspects related to the tool geometry. Increasing the tool shoulder diameter certainly increases the frictional heat being generated at the top by rubbing the tool shoulder with the surface of the workpiece. Similarly, the tool pin diameter, increasing the tool pin diameter also increases the deformation as well as the frictional heat, but this has to be done considering the thickness of the metal to be welded. Normal load does the two things. One is it ensures the plunging of the tool along the weld line, and it also facilitates the forging action and controlled movement of the material during the friction stir welding. Dwell time is about like the how long heat will be generated at a particular location, so that the sufficient softening of the metal occurs before traversing the the tool along the weld line for development of the weld joint. Then the plunge depth is the another parameter, like how far our tool pin is able to penetrate, or tool pin is penetrating into the base metal. So, usually what we do, like say if this is the joint line, okay, and this is the pin which is penetrated, and this is the shoulder, okay. So, the tool pin is allowed to penetrate like say little less than the thickness of the sheet. So, that may be like 0.3 to 0.5 less than the sheet thickness. That is about the kind of the plunge depth that is realized. And so, these are the various process related parameters. So, this slide basically shows the different steps schematically what I have already said. This is the tool, this is the shoulder, this is the pin, say this is threaded cylindrical pin, the tool is rotated, say and the top view location is this, okay. So, the rotating tool is plunged, say, so it penetrates along the weld line, okay, at the same location, and when it is penetrated, obviously the heat will be generated due to the friction and the deformation. So, this will be causing the softening of the metal. So, now the say penetration is complete, and this will be generating the maximum amount of heat, and this here what we do, we allow to rotate the tool at a particular location for longer time, that is the dwelling stage. This was the plunging stage, okay, and this is about the tool rotational stage. Okay. Once the dwelling is over, means the dwelling tool will be allowed to rotate at a particular location until the sufficient heat is generated for causing the thermal softening of the material, and then tool is allowed to move along the weld line. So, in this when the tool is started to move, then only the movement of material from one side to another will be taking place, from front side to the back side or back side to the front side, okay. And once we reach at the end, the tool is retracted. So, the last stage will be after traversing, tool is retracted, and that in turn will be leading to the development of the joint. So, when the joint is developed, we will be getting the 4 zones basically. If we see base metal, okay, this side, and the neighboring area will be like heat affected zone, and very next to the nugget zone, weld nugget zone, there will be TMAZ, thermomechanically affected zone, and then the weld nugget. Weld nugget is the zone where dynamic recrystallization will be taking place, and equexed grain structure, equexed very fine grain structure will be produced. But in the thermomechanically affected zone, it will be having some effect of the plastic deformation coupled with the heat, but this zone is extremely thin. Then very wide heat affected zone, depending upon the amount of the heat that has been generated during the welding, and that is what we can see in this enlarged view. If we see this in enlarged view, so the fourth zone is the base metal, then we have third zone is the heat affected zone, where which has been affected by the heat, and then the zone next to the weld nugget, zone 2 is basically TMAZ, thermomechanically affected zone, and the finest grain structure will be there in the weld nugget, okay. And this happens primarily due to the dynamic recrystallization, okay. So, the coarse grains will be there in the heat affected zone, and very fine grains will be there in the weld nugget zone in case of the frictionist weld joints, okay. Now, so as far as the friction welding is concerned, this is another solid state welding process. So, again in the friction welding, heat is generated by the friction coupled with and the deformation that will be happening at the interface. So, say these are the two components, base metal A and B to be joined. So, what we do, one end is kept fixed and another end is rotated in firm contact with each other and under the certain normal load. So, when it is rotated, the heat will be generated at the interface by friction, okay. So, once enough heat is generated, then the forging force is applied for upsetting purpose, and once this upsetting is done, the joint is developed. So, basically there are two main stages. One is the rubbing, during which the heat will be generated due to the friction coupled with the deformation, and the second is the upsetting, during which the significant plastic deformation and forging action will be involved. So, how the things change during the friction welding, that is what we can See, as far as the so the process basically in the initial stage, what happens when the rubbing starts, the initially frictional heat will be generated, but at the same time whatever the impurities which are present at the interface, they will be removed. So, self cleaning will be there, and then there is a possibility of differential heat generation at the center and at the outer surface. So, we know that the frictional heat generation will be there minimum at the center due to the minimum relative velocity between the components, and the maximum relative velocity will be there outside. So, because of this we may have low temperature at the interface and the maximum temperature at the outer surface. So, that is what happens due to the differential heat generation. So, if the differential heat generation is very high, then it is possible that the forging action may not happen at the interface, and that can promote the presence of defect at the interface. And if say this is not the scenario and sufficient temperature across the interface is attained, then increased forging force is applied for realizing the upsetting and develop the joint like this. So, this upset zone is machined out later on to get the desired geometry. So, if we try to see the different process related aspects and the parameter variation as a function of time, this is the constant speed drive system, where initially speed is increased, then it is continued to rotated under the frictional effect, and so that will be generating sufficient heat, and then initially the friction will be less and that will be maintained, friction force will be maintained, and then the force is increased. So, this is the frictional zone, and then force is increased for upsetting purpose. Then that will be because so initially the reduction in upsetting length is will be increasing gradually during the frictional phase, and then when the upsetting force or forging force is applied, upsetting happens very rapidly as a function of time. Okay. So, these are the different stages as far as and the process parameter related aspects. So, when the joint is developed depending upon the the joint friction weld joint depending upon the kind of the metal system. So, since significant plastic deformation coupled with the heat generation. So, when the plastic deformation coupled with the heat generation in metals like steel, what it will facilitate the soft phase like ferrite or pearlite transformation into the martensite. This is one. It will also facilitate the work hardening. Okay. So, when both these things happen, usually it causes the significant increase in hardness at the interface. The same thing happens also in the work hardening metal, but due to the severe plastic deformation at the interface, fracturing of the fine precipitates in case of the pH metals will be happening, and the heat generation will be causing the reversion and a recovery of the metal. So, that will be causing the softening at the interface. So, depending upon the kind of metals that we are dealing with, various kind of things can happen due to the plastic deformation and due to the heat generation at the interface. So, there can be work hardening at the interface or transformation hardening at the interface depending upon the kind of temperature attained, followed by the cooling rate. There can be reversion of the precipitates at the interface and the heat affected zone due to the heat being generated, and things there can be recovery in the heat affected zone if the metal is in the deformed condition. Okay. That recovery will be softening the material in the heat affected zone, and the recrystallization at the interface and excessive heat generation can promote significant grain growth. So, all these metallurgical changes can occur in the joint developed by the FSW. Ultrasonic welding is the another one where like say which relies basically the interfacial frictional heat generation. Okay, interfacial heat generation. So, how it is done, like say mostly this is used for development of the lap joints like this, the metal A and metal B in lap configuration. So, there is a tool, okay, through which the ultrasonic vibrations will be applied with the help of the sonotrode. Okay, and this tool will be kept under the normal load. Normal load will be applied with the help of the tool, and the tool will also be applying the ultrasonic vibrations. So, this combination of the normal load coupled with the ultrasonic vibrations which will be providing the lateral movement, that develops the interfacial, that causes the interfacial friction. Because of this interfacial friction, heat is generated, and that tends to deform the material and facilitate the flow of the material. So, the interfacial flow of the material causes this first improves the metallic intimacy coupled with the mechanical interlocking, and heat generated will be facilitating the development of the metallurgical bond through the recrystallization and the phase transformations. Okay. So, heat generated at the interface will be function of the normal load, greater the load, greater will be the heat generated. Likewise, the frequency, greater will be the heat generated, and direction of the oscillatory motion. Usually, vertical movement is used for the ultrasonic welding of the plastics, but the lateral movement is used for the metal to metal joining. Okay. So, these are about the various aspects related to the process parameters. Now, energy being delivered during the ultrasonic welding E is found to be the function of the energy required for the ultrasonic welding is found to be the function of the sheet thickness and hardness of the material. Greater the hardness, greater the sheet thickness, greater will be the energy required for the welding purpose, okay, ultrasonic welding purpose. So, here we know that at the surface there will be variety of impurities, and these impurities, when these rub each other, can be removed or can be taken care of, but still we want the proper cleaning of the surfaces. Okay. So, now here I will summarize this presentation. In this presentation, basically I have talked about the mechanisms that play significant role in solid state joining, and also about the principles and process parameters associated with the ultrasonic welding and friction stir welding and the friction welding processes. Thank you for your attention.